some non-trivial geometry or geometry with the horizons.
Yeah, so that's what it would seem to be suggested by this. If you have trivial topology in the bulk.
What about vice versa? If I have non-trivial topology of any horizons, is it always dual to some mixed state on CFD?
If I have non-trivial topology, is it?
Or any horizons, is it always dual to the mixed state?
Yeah. So I guess one should check that. So, as long as you can find subsystems such that the entanglement entropies computed with that condition are different, that would suggest it always has to be a mixed state. That's right. Yes. Yes. Any other questions related to last time? Sure. Yes. Yes.
Do you have an idea of how to associate entanglement entropy to a subregion in this kind of state?
Right. So yeah, in this case, we have some field theory state, and again, we could compute entanglement entropies. But I think it goes beyond the scope of what Ryu Takenagi tells us how to do. So, so if I have some state psi which is just dual to some superposition of one geometry and some other macroscopically different geometry, yeah, I suppose one could try to come up with a proposal, but I don't know of an existing proposal off the top of my head. Yeah, it's an interesting question. Look at.
Can I ask a very specific question?
Yes.
How should one in nonlinear theory understand superposition of geometries?
How should one understand superposition of geometries?
In nonlinear theory of gravity.
Well, the classical equations are nonlinear, but so what we apply quantum mechanics to nonlinear systems frequently, right? It's a different type of linearity. The linearity is in the state space, so it's okay if the classical equations are nonlinear. That doesn't conflict in any way with.
But on the purely geometric grounds of the classical GR, how would you?
Well, so I
decipher geometry that corresponds to the whole superposition
yeah.
at once.
So I think the only conflict would be if you assumed that there should be some classical geometry that corresponds to the superposition of two other classical geometries. Okay, and I think that's not true. Yes. Sorry, say again?
Isn't this equivalent to calculating for CFD with finite n, where you don't have classical geometry, you have some highly defined?
Well, yeah, if you had finite n, then you would probably always be in this situation. Whereas, with large n, at least we can have some states that are well described by a saddle point geometry. So, but at large n, I could still consider a superposition of two classical geometries. Yeah. I had direct orders from Eliezer. But
You have instructions.
does someone have a way to get in touch with him?
If you allowed it to start at 2:15, it should start. Is that here? Because
Well,
you can never tell when he'll arrive.
his specific instructions were to wait until he got back.
Yeah, you never know when meetings
You
are,
think
and then
we should start? Okay, but okay. I mean, as long as the other organizers take the responsibility to override the instructors. Okay. Okay. Ami. Okay. 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 So for the record, Eliezer, if you're watching this, I've been forced to start against my will.
Yeah, I allowed you to start.
Okay.
Started already?
I'm just starting now.
Good, because David and Eliezer phoned me that they are delayed.
Okay. Okay. So. Okay. 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 All right. Well, thank you for the message. I will begin. So last time we talked about various properties of entanglement, and by the end of last lecture, we had understood that entanglement entropy in holographic conformal field theories is at least conjectured, and with various pieces of evidence, to correspond to some geometrical observables on the gravity side. Okay, and if this is true, it's sort of a beautiful piece of the ADS-CFT dictionary, because if we think about all possible theories of gravity, what's universal in them would be that you have some geometry. Maybe there are various other fields in different examples, or some examples have strings, some of them have branes. But the one thing that we expect in all the examples as a universal kind of observable would be geometry. And in the on the quantum mechanics side, entanglement is in some sense a universal quantity that we can look at in all theories. Whereas if you look at say correlation functions or Wilson lines or something, that would depend on which of those observables exist depends on which theory you're talking about. Okay. So today I'm going to talk about more general connections between field theory entanglement structure and space-time structure. And I want to start by understanding better the structure of entanglement in quantum field theory states and in conformal field theory states. Okay. So I'll describe a calculation of a density matrix for a subregion in a quantum field theory. And it's convenient to use path integral methods for that. Okay, so let's start by considering some quantum field theory. I'm not specializing yet to conformal field theories. Okay, actually, the first bit applies to even more general quantum systems. I want to start with the full theory in a thermal state. This is eventually I'm going to be interested in starting with the vacuum state and computing the density matrix for some subregion. But I'll be a little bit more general and start with a thermal state of the full system, and we can take temperature to 0 if we want later on to get the vacuum state. Okay, so the density matrix for a thermal state is this canonical ensemble density matrix that I wrote down before. Okay, and now, so this is the space that my field theory is living on, and now I want to consider some subspace A and compute the density matrix for this subspace. Okay, so we can represent these things using path integral methods, and so I'll remind you that because this is the operator that evolves us forward by an amount beta in imaginary time, then psi 2, so the matrix elements of of this density matrix in a field space basis are described in the usual way by this Okay, so the usual way that we pass to the path integral description. So this is described by this path integral, and I can draw a picture to represent that. So, okay, so the matrix element between phi 1 and phi 2 of this object is this path integral where we start with some state psi 1, and so this is our boundary condition at imaginary time 0, and we evolve forward by an amount beta in imaginary time, and then we demand that the fields are equal to the phi 2 at the end. Okay, and if we take this and now set phi 1 equal to phi 2 and integrate over all possible values, that gives the standard result for the path integral of the description of the partition function. Okay, so for partition function, which is defined to be trace of e to the minus beta h, we do this set. Okay, and that now gives us, instead of this picture, we can draw this picture, okay, where we've basically identified these 2 points. Okay, so now instead of calculating the density matrix for the full system or the partition function, I want to do something halfway in between. I want to calculate the density matrix only for this subsystem A. Okay, and so that's going to involve tracing. So to calculate the partition function, we traced over the entire set of degrees of freedom. To calculate the density matrix, we just want to trace over the fields outside of the region A. Okay. So for row A, what we want to do is now consider this matrix element So we want to take the fields outside the region and identify those, identify these. This corresponds to tracing over those, and we integrate over these, but we leave these ones unfixed. Okay, so then the picture looks like this. So it's a path integral now where we have so this thing, which up to the overall constant is the matrix element of our density matrix for the subregion, corresponds to this particular path integral. So I'll write that out explicitly, d phi e to the minus s, where psi for this is the B region of 0 is set equal to psi for the B region of beta, psi for the A region at 0 plus is equal to psi 1, and psi for the A region at beta, or sometimes I'll call that 0 minus, is equal to psi 2. Okay, so that's the path integral description for the, if you start with a thermal state, and then you calculate the density matrix for this subregion A. Okay. Now, I might just be interested in the vacuum. Okay, in which case, I take the previous expression and now just take beta to infinity. Okay. Okay, and so what that looks like is the following. So it tells us that this density matrix for the region A in the vacuum state is equal to this path integral, where now we have an infinite amount of imaginary time with these boundary conditions that above this region we're interested in, we have psi 1a, and below the fields are equal to psi 2a. Okay. So, so this has, we're going to use this now in various applications. Let's see. Okay, so using this expression for the density matrix, one thing we can do with this, and I think I'll postpone talking about it, would be to calculate, okay, we can calculate explicitly these quantities trace of rho to the n. So this involves, okay, so this is this matrix element. Trace of rho to the n basically says you take n of these, and then you identify, and then you trace over them. So you identify this this field here with the field here in the next one, and so forth. And that corresponds in this picture that I've drawn to now just taking the fields below this cut to be equal to the fields above this one, and below this one to be above the next one. So it's like this. So it corresponds to doing the path integral on some multi-sheeted surface with n sheets. Okay, so if you wanted to calculate trace of rho to the n using a path integral, we just evaluate the partition function. Well, okay, so let me be careful. There's some factor of z there. So if I want to calculate trace of z rho to the n, I calculate the partition function on this multi-sheeted surface, where the branch cut is the region that we're interested in. Okay, and so I might as well just finish that thought and tell you then that a way to calculate the entanglement entropy using a path integral is actually just to calculate this for all possible n, and then either, okay, so the standard way is to analytically continue this. So SA, which is trace of rho log rho. So that's equal to the derivative with respect to n of trace of rho to the n at n equals 1. So if you can calculate all of these and analytically continue to real n, take the derivative, and then set it n equals to 1, that would give you the entanglement entropy. There's actually another way to do this without analytically continuing. So I'll write down a formula. Okay, so one can write a kind of an integral formula that achieves the same result. Trace minus 1. So the fact that this is equal to this follows from the fact that this integral dA over A okay, so we use the fact that this integral equals this, and then we replace x with rho and take the trace. Okay, so this formula could be useful in cases where perhaps you're calculating these entanglement entropy, these trace of rho to the n's numerically, and you don't have a way to analytically continue. Okay, so going back to our there might not be an analytic continuation.
There's no way you could create one out of that.
So good. So yeah, this should work. Okay, so the statement is that in some cases there's no analytic continuation. So how could you possibly get something sensible? And I think in this case there's some problems with the convergence of this formula. So but assuming that there is an analytic continuation and you just don't have a nice enough expression to figure out what it is, you could use that formula to calculate the entanglement entropy by brute force, which could be useful for something. Okay.
Sorry, does that sum converge?
Pardon?
For typical identity matrix, does this sum over n converge?
Yeah. So at least I had a conversation with Zidong about this issue, and he claimed that when the analytic continuation exists, then this will be well behaved as well. So one could do examples where the entanglement entropy is known, and you can get the same result by either method.
But there are examples in which you will compute it for every integer n, such as you know, that integer liquid.
Uh-huh.
And at some point in the moduli phase of the two intervals, there is no known analytic continuation.
Oh, so
I don't know what the Von-Neumann is, even though all
I
the
see.
entities are known.
So maybe this is useful then. I mean, one should.
There is no analytic continuation.
But if there is an analytic continuation which is just not known, then perhaps this will give you the result. So one could check whether this converges. Yeah, that could be interesting. Okay. Yeah.
If that does diverge, could you use some sort of trick with Riemann-Zeta functions to just get the part that we're interested in?
I don't know. Okay. So I want to use. Okay.
Replace the summing and then the integration there?
Um,
Formula for AC?
I think you have to sum first and then integrate if it's going to work.
Because it doesn't.
Yeah. Yeah. Okay. Okay. This was supposed to be an offhand remark, but I'm going to erase it now.
I think it's not as an offhand remark. Usually in quantum field theory, objects that will come out behavior and they were turned out to be interesting, they have a path integral representation. And this is an object for which there is no path integral representation, so it's suspicious.
Oh, you think the entanglement entropy in general is this?
And we know that they exist at the end of the day after the dust settles,
Mhm.
are objects for which there is a path integral representation. And for the Von-Neumann entropy, there isn't one, as far as I know.
Mhm. I mean, this could be related to the divergence issue.
No, but
So one has to be careful.
But in the end of the day, they're interesting. There is a path integral representation for them. Like the Wilson node has a path integral representation. A surface operator is one. Correlation functions is one.
But these trace of rho to the ends have a path integral representation.
This Von-Neumann entropy.
Okay, but in some sense, the trace of rho to the ends should be equivalent to the entanglement spectrum for the theory, and the von Neumann entropy is some particular number you can calculate using that spectrum.
But not at the continuum limit. Even if you
Mhm.
do all the rho to the end, it does not mean that rho log rho has a continuum limit. Objects that have
Mhm.
continuum limits in the end of the day.
But I mean, we know
they have a path integral
yeah,
representation.
okay. But we know examples that have a so the S itself doesn't have a continuum limit, but we know examples of. So I mentioned last time, taking the derivative of S with respect to the length has a nice continuum limit.
For one interval, it works.
Mhm.
More generally, yes, no.
Okay. Okay. I wanted to calculate, as an example, the density matrix for a general quantum field theory in Minkowski space where the regions that we're going to be interested in are say the region to the right of the origin, or some point which we'll call the origin, and the other region to the left of the origin. I'm drawing a two-dimensional picture where this is time, but we could have some other coordinates. Okay. Essentially, all of the examples where the density matrix for some subsystem in a quantum field theory is known reduced to this one. So when we talk about conformal field theories later, we'll talk about density matrices for a ball-shaped region, and that just will follow from this calculation as well. Okay. Good. So I want to use this technology that we've developed. Okay. So this suggests that I should just draw the picture. Remember, the picture was we need to calculate. Okay, so this is the region that we're interested in, and so to calculate this density matrix, we need to set the field equal to phi1 r at 0 plus, and equal to phi1 phi2 r at 0 minus, and then perform the path integral. Okay, and maybe I'll skip writing down the integral expression. Okay, so there's a nice way to think about doing this, and that is to introduce a different type of coordinate. So we introduce an angular coordinate when we're doing our path integral. Okay. And then I could say that the expression that I had over there okay, so we think of integrating in this manner, where you have phi1 here and phi2 there, and so that gives us this expression Euclidean, where phi theta equals 0, phi1 r, and phi theta equals 2 pi equals phi 2 r. Okay. So now I'm going to make an analogy with something that we've seen already, which is just a thermal the path integral expression for a thermal density matrix. So if I draw this picture in a different way. Okay, so we're really integrating from theta equals 0 to 2 pi. Okay, so I'm drawing theta and a radial coordinate, and we have phi 1 r, and we have phi 2 r. Okay, and so this looks like the very first expression that I wrote down at the beginning of the lecture, where we were writing down a path integral expression for for the matrix elements of this thermal density matrix. Okay, and so we could recognize this path integral as being the matrix elements of a different kind of thermal density matrix, or a thermal density matrix with respect to not the ordinary Hamiltonian, but the operator that's going to generate evolution in the variable which is related to theta by an analytic continuation. Okay, so this one was the matrix elements of e to the minus beta h, and so this one should be the matrix elements of e to the minus 2 pi, because we're evolving by 2 pi, h eta, where this is the generator of evolution in I theta. Okay, this variable eta, which is I theta. Okay, so what is the interpretation of this eta? Okay, so if we write down, so if I write down the metric in this plane, and then I analytically continue theta back to eta, this gives me dr squared minus r squared d eta squared. Okay, and and this turns out to be the coordinates on a patch of our original Minkowski space. Okay. So we started with this field theory on Minkowski space, and we were interested in calculating the density matrix for this half space. We found that the matrix elements of that density matrix are the matrix elements of this particular operator, and now we just have to interpret what eta is. And so eta is the thing that people might call Rindler time. Okay, so it's a time-like coordinate that basically looks like this, that flows in what we call the right-hand Rindler wedge. Okay, so h eta, just in terms of its action on coordinates, looks like this. Okay, and it's sometimes called the Rindler Hamiltonian. Okay, and it's basically the boost generator. So you can think of it as generating accelerated trajectories, or it would be the Hamiltonian for an accelerated observer. Okay, and so the statement, our conclusion, that the density matrix for this right-hand side is a thermal density matrix, okay, with respect to this particular Hamiltonian. Okay, this is one way of getting to the statement that accelerated observers would see thermal physics, even if you're in the Minkowski space vacuum. Okay. Okay. And using this, okay, so this should be translated into some quantum operator if we want an explicit expression for h. This will be useful in the next lecture. And so at t, I'll work at t equals 0, where now it reduces to x times the time generator. Oh, sorry, I should have. This is the local expression, but the quantum operator is x times t0, 0. Okay, so that's the summary. We started with an arbitrary quantum field theory on Minkowski space, and we showed that if I want to calculate the density matrix for the right half space, then what I end up with is a density matrix which is thermal, not with respect to the ordinary Hamiltonian, but with respect to this Rindler Hamiltonian, which generates a time evolution restricted to this Rindler wedge. Okay. I missed. Okay. So if we start with the vacuum state of this Minkowski space field theory, then I can say that the density matrix for the right half space is what I wrote over there. I'll write it in a different way. And then we have a similar expression for the left half space. L. Okay. And so these represent ensembles. The two halves are in a mixed state. And of course, since we started with a pure state, there must also be a way to represent the full state as an entangled state of the two sides. Okay. And there's actually a simple expression for that as well that you can check. Reproduces these formulas. So we can write the full state as the following entangled state. Okay, so it's just really this sum should be an integral, but other than that, we're just summing over the possible energy eigenstates with respect to this right-hand Rindler Hamiltonian, and we take the corresponding state on the left-hand side, and then we add them all up with this Boltzmann type factor. Okay. In free field theory, okay, you can open up Burrell and Davies to see this calculation done in a different way in free field theory. And an interesting thing there is that we can then define particular modes living on the right-hand side and equivalent modes living on the left-hand side. And what you find is that every mode on the right-hand side is entangled with the corresponding mode on the left-hand side. Okay. And as an aside that may be useful for Joe's lectures, if I try to remove that entanglement, okay, so if instead of this state, I try to replace it with a state that is just a tensor product, okay, where these modes are not entangled with each other, one can show, at least in the free field theory case, that we end up with a singular stress energy tensor on these what are called Rindler horizons. Okay, so that may play into some things that Joe will tell you about. Okay, so I want to go back towards ADS CFT. And so let's start just by making some statements about CFTs. Yeah, question.
Before you head on, is there a unique entropy in this 1 plus 1 dimensional case associated with this Rindler horizon that you can write down associated with these density metrics?
Well, it's yeah. I mean, I could calculate the entanglement entropy here. In this case, it's divergent as usual, but yes, you could just
divergent in the 1 plus 1 case. Is that because this is 1 plus 1 dimensions of space-time?
no. I mean, generally speaking, as I said last time, when you calculate an entanglement entropy for a region in a quantum field theory, there's some UV divergences in that, and what you should do to talk about sensible quantities would be either to compare entanglement entropies between different states, or to calculate the derivative of the entanglement entropy with respect to the size of the region, or you can calculate things like mutual information that combine entanglement entropies for two different regions and the union of the region, or you subtract SA plus SB minus SA union B, and that would be finite. Yes? Yeah, that's what I'm going to say next. So in conformal field theories, we can use this result to calculate the density matrix in a lot of other situations. Okay. So for example, you can use a conformal transformation to map this right-hand Rindler wedge to an arbitrary to this causal completion of an arbitrary ball-shaped region. So in the two-dimensional case that I'm drawing, this is just an interval. In the higher dimensional case, this would be a ball-shaped region, and then this would be the causal completion of that. In the ADS CFT context, sometimes we'll be interested in this mapping that takes Minkowski space to a diamond on the boundary of a cylinder. Okay, so this is S. This is SD. This is R. Okay, so there's a conformal transformation that takes the entire Minkowski space to this diamond-shaped region. If you unfold that, this region is a diamond on the boundary of the cylinder. And in that case, this wedge right here maps to a diamond covering 1/2. And the other wedge maps to a diamond covering the other half. And I actually have a nicer version of that. Okay, in full color. Okay. So, so we have this conform. I'm still just talking about the CFT, so you should ignore the interior of this cylinder. This is just a CFT living on a sphere times time, and this region maps to this, which is really okay. So if I look at this red region, what it is the causal completion of a hemisphere. Okay, so this, if I draw a time slice, so that's a sphere, and the red region covers one hemisphere, and the green region covers another hemisphere. Pretend this is red. Okay. Okay, so now we want to. So now, in particular, I could take these statements, okay, and use the conformal transformation. And so, what I would learn, for example, would be that the density matrix for a hemisphere of a CFT on a sphere is thermal with respect to an operator that generates the image of this Rindler time over in this picture. Okay, so that's that's something that looks like this. Okay, so there's a particular generator in that diamond, okay, which is a time evolution that exists only within this diamond. I can write down explicitly what that generator is, and I can write down the quantum operator corresponding to that. Okay, so we can explicitly write down the density matrix in this case. Okay, so let me do that. Okay, so this gives us a different representation of, so rather than just saying that pure ADS is dual to the vacuum state of the CFT on the sphere, okay, we can understand a little bit of, we can sort of decompose that and say that the pure ADS is dual to this entangled state of the left and the right halves of the sphere, which looks like this. Where now these E's are eigenvalues for this other Hamiltonian. I'll call this time coordinate chi, and so the H would be the generator of chi. Okay, and so similar to this, we can write down the two density matrices. So the density matrix on the left is 1 over z e to the minus 2 pi h chi left, and the density matrix on the right is 1 over z e to the minus 2 pi h chi right. Okay, so the interesting thing here is that with this particular choice of decomposition of our spatial geometry that the CFT lives on, the information about the quantum state breaks up in a particular way. So here you have a pure state. And what we have here is a statement that to this half you can associate a density matrix. That's some part of the quantum information about the state. To this half you can associate a density matrix. That's another part of the quantum information. And knowing just those two density matrices doesn't tell me everything. What's left is the information about specifically how these degrees of freedom are entangled with each other. And so the question I want to ask now is, well, given this decomposition of the information into this part, and this part, okay, how does, can we translate that in a nice way to the bulk information? Can we say that this density matrix encodes a certain part of the bulk information, and this encodes another part, and this encodes another part? Okay. So what info geometry is contained in row right and row left, and then the entanglement information would be whatever's left. Okay. Okay, so I'm going to give a plausible answer, and then I'll make some arguments for the answer. Okay, so the plausible answer is that this density matrix row right contains the information about a certain wedge of the bulk geometry, which is this wedge here. Okay, so that's one way to describe that wedge, is that it's the intersection of the causal future of this boundary diamond with the causal past of the boundary diamond. Okay. There's other equivalent ways to describe what that wedge is, but let's take that for now. This is also the part of space-time that is accessible to some particular accelerated observer in the bulk. So we could think of this actually as a Rindler wedge of the ADS space-time. So the proposal is that this density matrix describing this diamond over here tells us everything about this Rindler wedge, and the density matrix over here tells us about the other Rindler wedge, and then entanglement would tell us about the rest. Okay, so I have to tell you now why you should believe that. Okay. Okay, I'll write that down. So row R carries info about Rindler wedge of ADS. Okay, so the first thing is to think about what you could calculate given that density matrix. Okay, so given that density matrix, you could calculate any observable involving either local operators or non-local operators, as long as the operators have support within that region. So I could compute any correlation function in this region, or Wilson lines, or these. We could compute entanglement entropies for subregions of this region over here. Okay, and so that's a lot of information. One thing in particular that we could think about doing would be calculating a response function, okay, where we perturb the field theory at some time down here and then calculate the response to that at some later time. Okay. Now, suppose that we had a small perturbation to the bulk geometry anywhere inside this wedge. Okay, so actually what I want to imagine is that someone goes inside the wedge and places a tiny mirror at some point anywhere inside this right-hand wedge. Okay. So now, when we're calculating this response function, there's going to be some point down here I can choose, such that if I perturb the CFT here, which we can think of as making a local perturbation out on the boundary in the bulk, so that signal is going to propagate, hit the mirror, and we should find a big response at some particular point up here. Okay, so anything in this causal wedge here, it is reasonable to expect that we'll have observables that are sensitive to changes, even if they're very local changes. Okay, we could also talk about calculating entanglement entropies, and those should give us the areas of all sorts of surfaces inside this wedge as well. So So at least for things happening inside that wedge, it seems very reasonable to expect that we could, we would be sensitive. We would have the information about those things just by knowing this density matrix. Yes?
You mean that you can evaluate it either in just the right density matrix or the pole, the answer will be the same?
Yes, yeah. So if I ask about a correlation function which is restricted there, or an operator expectation value which is restricted to the right-hand wedge, then okay, that corresponds to calculating in the full theory the expectation value of an operator that looks like this, where this corresponds to the left-hand side. And to do that, we don't need to know about the left-hand density matrix at all. This just reduces to trace of rho right times O right. Okay. Yes?
If I was an observer in the right wedge, and if I was an eternally accelerating observer, then the fact that this is thermal density matrix tells me that I will see thermal radiation, right?
Sure, yes.
If I was not eternally accelerating, but let's say I stop accelerating at some point, with knowledge of this rho r, do I still get to say something about local physics for such an observer?
Yeah, I mean, this is a different sort of question. I mean, asking what particular observers will see in that wedge, depending on their trajectories, is maybe a more refined question than the type I was talking about. But I guess in principle, one should be able to understand the answer. I'm not sure how to do that in practice. Okay, so what about now? Some perturbation that happens outside that wedge. Okay, so I want to ask, yes?
Do you have explicit calculations that you can do inside that wedge
Using the density matrix. Yeah, I mean, absolutely. I can calculate any correlation function. So in particular, I can calculate correlation functions whose result tells me about the lengths of geodesics. I can calculate these response functions that I was mentioning, which should be sensitive to paths like that. I can calculate entanglement entropies, which should tell me the areas of various curves. So I can densely fill this region with quantities that I have boundary. I have the technology to compute on the boundary. Okay. So I'm now going to argue, though, that anything outside, for anything outside here, we cannot possibly deduce the local physics based on just knowing this right-hand density matrix. Okay, and so one argument is the following, and that's to consider states where I act with a unitary operator on the left-hand part of the state. Okay, so instead of the vacuum state, I consider this state where I act with a unitary operator on the left, and I leave the right-hand side alone. Okay, and so if I do that, then rho right is unchanged. Okay, but generally this will change the state of the left-hand side. Okay, so for example, I could act with some operator that perturbs the state of the CFT over here. Okay, and if I do that, this is going to then perturb the bulk geometry. Okay, and in general, by choosing where by perturbing the state at various points inside this green diamond, okay, I should be able to affect the bulk at least anywhere in the causal future or the causal past of that green diamond. Okay, so I could make a perturbation down here, and that could affect the geometry just beyond this Rindler horizon here. Okay, and so because of that, we could say that there's two different geometries, okay, which differ at points arbitrarily near but outside of this wedge, but they have the same density matrix for the right-hand side. So it can't be that the density matrix for the right-hand side has the information about the geometry beyond that Rindler horizon. Okay, so in some sense, for this example of ADS, this particular wedge is the minimal plausible, the maximal plausible set of information that we'd have about the bulk geometry. Yes? Okay.
This seems pretty simple because the CFT lives on a sphere.
Yes?
Can you say how it can generalize to a plane or the types of diagrams and so on?
Well, if you want, remember that a part of this whole thing, there's actually a way to think about, this blue line here delineates the boundary of a Poincare patch of ADS. Okay, so if I take that wedge, it's easier to see if I draw this side view. Okay, if I draw this side view, then it looks like this. Okay, and then there's a wedge. Okay, and so everything I just said, you can interpret. So that Poincare patch in another set of coordinates, it looks like the planar case. And everything I just said, you can interpret it in terms of the planar language as well. Okay.
Second question, how would this look if you chose a space-like surface? Could you have chosen a light-like or a
If I chose, so which surface do you want to modify?
the circle?
The circle. Okay. Well, if I have to choose, if I want to think about the fields at different points on that circle as being independent degrees of freedom, I have to choose it to be space-like. Okay, if I look at a time-like surface, then the fields at those different points are not independent of each other. They're not independent degrees of freedom. Okay, so the game here is to divide up the degrees of freedom of my field theory into some independent sets, look at how they're entangled with each other, and then look at how the density matrices map onto the geometry. Okay. Okay, so that's the okay. That hopefully motivates the fact that this answer is plausible. That a row right carries the information about the Rindler wedge of ADS, and row left carries the information about the other Rindler wedge.
Having acted on the left-hand side with this unitary operator,
Yeah.
you've also modified the ADS geometry here, right?
Yes.
You've modified the inputs. Do you still have a proper picture like the one you've drawn inside? I mean, this picture gets modified in certain fashion.
Yeah, that's right. So the simplest thing would be we could just have a gravity wave that goes up from here. Maybe it comes up and it bounces off and it goes up there. Okay. So the idea is that states where I have the same row right but a different row left, states like that, they would look like geometries where you still have this one wedge, but the rest of the geometry might be different. Okay. Okay. So I'll summarize in a minute. Okay. Before I do that, I want to ask the question. Okay, so what's left over is this entanglement information. Okay, and I want to argue that is basically what is going to tell us about the rest of the space-time. And one of the ways I want to do that is to think about what would happen if I try to just remove all of that entanglement information. What happens to the space-time?
Hamiltonian for quantum field theory.
Yes.
Now you've extended that some, right? You're not just doing that field theory.
So I still have the full field theory on a sphere evolves using some Hamiltonian, the Hamiltonian for the CFT on the sphere. So really all I'm doing is now taking the state at a particular time, and I've just decomposed it. I've written it in a different basis, essentially, which corresponds to the two halves. And so we've just seen that this is like an entangled state of the two halves. It's kind of like taking a spin 1 combination of two spin half particles, and now I'm writing it explicitly as half minus a half minus a half half. And now I'm interpreting the density matrices for the two halves. Okay, good. Okay, so what if we remove entanglement between the two halves? Okay, so instead of considering this state okay, so remember, the density matrix for each half is like a thermal density matrix with respect to some Hamiltonian. Okay, and if we think of a thermal state, say of a bunch of particles in a box, well, I could just choose a typical state in that ensemble, and I should expect that for most simple questions, the answers, the physical answers, are going to be exactly the same. Okay, so I want to imagine doing that in this case. I want to replace this state with a state that looks like this, E left and E right, where E is a typical state in the ensemble row left, or E left is a typical state in the ensemble row left. Okay, so the first thing we can say is that all, okay, I have the same charge as this chalk brush, apparently. Okay, so the first thing we could say is that all of these observables, so remember, the way that we deciphered what was in this right-hand wedge was to calculate things like the trace of our density matrix times operators that were, say, 2-point functions or correlation functions or other kinds of operations restricted just to that wedge. Okay. Now, because we've chosen a typical state in this ensemble, and we're just asking some simple question, this is a situation where we should expect to get exactly the same answer as we did in the case when we were working in the ensemble. Okay, so this is going to be approximately equal to this. And so whatever method that we use to deduce the physics inside that right-hand wedge, if we apply the method again, then it's going to give us essentially the same answers up to tiny, tiny corrections. Okay. So by removing the entanglement, we could say that the insides of the wedges should be largely unaffected. Okay. However, now I'm going to go back to something we learned yesterday. Okay. So let's look at this particular codimension 2 surface in the bulk. Okay. Now this surface in this ADS geometry was the surface that Ryu Takiyanagi wanted us to take the area of in order to compute the entanglement entropy between the two halves. Okay. So if we take their proposal seriously, and I now say that I'm going to remove the entanglement between the left-hand wedge and the right-hand wedge, okay, according to the Ryu Takiyanagi formula, that would mean the area of this thing has to vanish. That somehow the metric inside, so even though the wedges are unaffected, somehow when I get to the boundary of the wedge, something horrible has happened to the space-time geometry, and I now just have an answer of 0 for the length between this point and this point. Okay, and I could do similar things for other subregions like that are along this boundary. Okay. Okay, so that suggests that there's some singularity here. That would propagate forward and backward along here. Okay, and so the suggestion is that we get a singularity at the wedge boundaries, firewall, if you will, and no space-time beyond. Okay. Now, one could do some. There's actually a calculation one could do that's a little bit more controlled, where you start with this state, and it turns out that I can explicitly find the gravity dual of a state where instead of pi here, I change that to a parameter beta. So it turns out that I can decrease this parameter beta, thus reducing the entanglement. Okay, and what I find is that as I decrease beta, that the length of this actually gradually decreases. Okay, so there's actually a controlled way of decreasing the entanglement entropy where you see this.
So that is a purification of the right-handed density matrix.
Yes.
You say you can purify with a beta-dependent term, which
No, so I'm changing the in this calculation. I'm allowing the right-hand density matrix to change, but nevertheless I'm decreasing the entanglement from the original value down, and.
You mean increase beta, though, right?
Oh, I'm sorry. Yeah, so decrease the temperature. I should decrease the temperature, increase beta, and what I actually find is that the distance between these 2 points increases and that area decreases, and so roughly speaking, this thing is pinching off. Okay, but yeah, when I do that, this is not an example where the metric in the wedges is largely unaffected. It is also changed. Okay, so just doing this would correspond to leaving the wedges the same, but kind of dramatically changing the geometry as soon as you hit the boundary of the wedge.
So your unentangled thing is it's a topological black hole in a pure state. So this really is a firewall, right? I mean, the thing you called like a firewall really is a firewall.
Well, yeah. I mean, I'm just, if there's a technical, so I'm saying there's a singularity there at the horizon, and
I mean, it's a singularity.
if you want to call that, yeah.
It's a singularity horizon.
Yeah, it's a firewall. I'm not sure of the precise definition of the firewall, but
Singularity horizon.
okay.
But right, so this is it seems like a fairly. I hadn't realized it's a fairly strong argument. You use Takinaga, and you can derive the existence of the singularity horizon for basically pure states of the black hole.
Right.
I don't think my lecture is that. Okay.
Well, I mean, this is a different kind of black hole. Anyways, yeah.
It's a thermal state. The thermal state of the
Yeah.
CFT. Yeah, maybe you haven't explained yet that one side looks like a black hole. I don't know if you
Yeah, that's okay. So it's true that I explained yesterday in the tutorial session that there's a way to actually think about this geometry in the wedge. In some coordinates, it's actually the Schwarzschild black hole with a hyperbolic horizon geometry. Okay, so it is a type of black hole, and this statement can be rephrased as saying that the microstates of a hyperbolic Schwarzschild black hole have singularities at their horizons. Okay, which we said in our papers.
So there's some signature of that similarity that you can detect by approaching that point from the wedge, and so you can calculate it within the wedge.
So it's very difficult. Basically what you'd have to do is consider some operator which is so complicated that it can distinguish between the microstate and the thermal state. Okay, so if you are able to do that and you have an interpretation for the results of that, then maybe you could distinguish. That's actually probably so maybe the answer it'd be interesting to think about that. Like how complicated of an operator do you need, and can you translate that into a statement of how close you are to the horizon? Maybe you can somehow argue that it's the Planck length or something, but. I don't know. Okay, so let me summarize what we have so far. Okay. Okay. So we had various objects, and we now have some kind of geometrical interpretations of them. Okay. So we have a density matrix, row right, and we've argued that that is, in some sense, dual to this wedge of space-time that could be patched into various other space-times. It could be patched into pure ADS, or it could be patched into this geometry that has a gravity wave just beyond the horizon. And depending on how you purify it, what happens beyond the horizon is going to be different. Okay. Then we had this pure state. Okay. Yeah, so in the black hole language, this is the thermal black hole. This is the ensemble. The pure state is like the black hole microstate. So we took a typical state in the ensemble row, and we argued that that is something with singularities there. And then we had the actual purification state. And that was something where there was a well-defined geometry past the horizon, and the details of that geometry depend on exactly how you purify the state.
So if I calculate the entanglement entropy associated with a segment of, let's say, the right half, but almost cover the almost entire right half, but not quite.
Yes.
Then as it approaches the entire right half, we should suddenly see a drastic change from some
Yeah, right.
to 0.
Yeah, actually, that would be one way to approach. If you consider that expanding that interval until the point where that would be significantly different in the two cases, maybe that would give you a way to estimate how close you need to
But
get.
there's some way to estimate actually how close you can get so that it decreases by some significant amount.
Well, I think you need to. Yeah, you probably have to be careful with like regulating the field theory and everything. For finite dimensional systems, I think there are specific statements that you need to look at half the degrees of freedom in order before you have significant differences, so it's an order of 1 fraction of the degrees of freedom. Yeah.
I think my question might actually be associated with, suppose you increase the size of one wedge, you can decrease the size of the other wedge.
Oh yeah. Okay. So let me say that. That's the next thing that I'm going to say.
Can you restate the second statement? The middle statement?
The middle statement was the statement that if instead of a density matrix for this region, which we said was dual to this wedge of space-time with sort of a non-singular horizon that could be patched into other space-times, if instead of that density matrix we consider a typical state in the ensemble described by this, okay, so sort of a pure state of this wedge, okay, which is a little bit of a singular thing to do in field theory, you end up with, the argument was that you get a singular horizon, or that you get, instead of a horizon, you have a singularity. Okay, right, so the next question is directly tied into what I wanted to say. Okay, which is that there's really nothing special about like this half and this half, okay? So remember, every point in ADS is equivalent to every other point. It's a symmetric space-time. So if I take ADS, okay, so if I'm an observer in ADS and I happen to be somewhere and I say, okay, consider this point here and consider this plane, okay, that's separating me from the audience, okay. So then I can draw an equivalent picture. There's some Rindler wedge, and it looks smaller on this diagram, but it's not. They're all infinite size because it's an infinite distance to the boundary. So what I could say would be that for that particular choice of point and for that particular choice of plane, the fact that I can step from here to here and continue to see smooth space-time is precisely explained by the fact that this subsystem of the CFT is entangled with this subsystem of the CFT. Okay, so in some sense, for every possible point you want, you could explain this sort of local connectivity by a certain statement about entanglement. Okay,
But
and
if I'm given the row right or row left,
yeah.
and I want to construct this, so there is this purification of entangled state that gives you the whole space.
Yeah.
But is there only a unique purification?
No, so I could take another purification, and this was the situation. Okay, so in the simplest situation, another purification might have a gravity wave. Okay, so if I took my original state and then I acted with this kind of an operator that doesn't affect the right-hand side, but it affects the left-hand side, that might have a disturbance that we would see once we cross the horizon. I could also consider a purification to a completely different quantum system. So here it was a purification to sort of an equivalent copy, but I might also consider a purification to a system with many more degrees of freedom. And that would maybe correspond to that same wedge of, okay, so you'd have the same wedge with one cosmological constant in there, and supposing that I tried to purify it by field theory with a lot more degrees of freedom, you might have another cosmological constant, and then maybe there's some kind of a brane separating the two. Okay, so you could have lots of possibilities. Okay.
First, you would consider limit in which one of the wedges must be bandwidth and the other one shrinks 0 size. And attempt to turn one problem density matrix to 0 almost, and the vacuum state density matrix would almost correspond to the vacuum state of the full system, right?
Yeah, you have to be really careful with, like, so if we're talking about the continuum field theories without any cutoff, then you're always, I mean, they're conformal field theories, and you can always, do an exact transformation to make a really small thing back to any size you want. If you worked in a cutoff situation, then you could ask questions like that. Okay. All right. So okay, I'm doing fine. So just to sort of summarize some of the things that we've been saying in a different way. Okay, so to get the full space-time, we had this sort of thing. So another way to look at that is to say, well, okay, so we're taking a quantum superposition here of a bunch of things that look like this. Okay, so this is very interesting because we just argued that each one of that this thing is sort of a singular wedge, and this one is also some kind of singular wedge. And now, apparently, by summing up a bunch of by taking this quantum superposition of a whole bunch of these wedges, you actually get a big connected space-time. This is really just another way of saying that by entangling the two sides, you generate this part. So another way to say it is you take your two systems and you take a quantum superposition of the disconnected ones, and you get this connected thing. Okay, so now I want to put these ideas to a test. Okay, and this is a bit so historically, what I'm saying now, in some sense, started everything, and but I'm presenting it as if we didn't already know the answer to this. So I'm going to postulate the non-existence of Maldacena. he existed up until 2000, and then I think he didn't exist and write a certain paper in 2001. But okay, so so given all of this, what I want to do is test this idea that you can take two systems and by entangling them, you're connecting up the space-time. And I'm going to do the most dramatic possible thing, which is to take two absolutely independent physical systems. Okay, one CFT on a sphere and another CFT on a sphere. With absolutely no interactions between the two conformal field theories. Okay, and I want to just write down exactly the same state. Okay, I'm going to do exactly the thing that connected this wedge with this wedge. There's two CFTs, different CFTs. Okay, so 1 and 2. And so if they're both in the vacuum state, then I just have two completely unrelated ADS spaces. Okay, but now I want to put them in the same state that we've been talking about all along. Okay.
You assume they're the same spectrum, or how can you do it?
They're the same CFT. Oh, yeah, okay, sorry. Yeah, they're the same, okay. They are different copies of the same field theory. Yeah, yeah. So they don't have different parameters, but they are different theories. Yeah. So we put them in a state, and so as before, both individual CFTs are sitting in a thermal density matrix, which we discussed, I guess, 2 days ago, and we said that the dual of a thermal state in the CFT is a black hole. Okay. But we weren't very precise about what we meant by a black hole. We didn't specifically say it was the black hole up to the horizon, or it was the black hole including something behind the horizon, or it was the black hole including a second asymptotic region. Okay. Well, now we're going to be more precise about that. Okay. So I guess based on everything we've discussed so far, it would be reasonable to say that this thermal density matrix for the CFT is dual to a black hole right up until its horizon, but not beyond. Okay. However, if I consider that whole state, so what Maldacena argued, okay, so those two density matrices, okay, correspond to these two black holes up until their horizon. But of course, there is a natural way to join those into a full geometry. There's this canonical maximally extended ADS Schwarzschild black hole. Okay, and so what Maldacena said is that, well, this particular state is the natural thing to associate as the CFT dual of this maximally extended geometry. Okay, so because this thing, it has on both sides it looks like a black hole, but it's now connected, and that's exactly what's happening. You have a thermal state on both sides, and the full thing is this entangled state between these two sides. So Maldacena suggested that these two things are related to each other. And in terms of the spatial geometry, what's happened is that you started with two CFTs. That means you have two asymptotically ADS regions. And if I look at the spatial geometry, what's happened is that those two asymptotically ADS regions are now connected by some wormhole. Okay, and so this is this was the thing that I guess when I started thinking about all of this stuff, this was the statement that I found really interesting. That you could just entangle these two CFTs somehow, and magically you get a geometry where the two sides are connected. Okay. So I think that's the most. It's in some sense the most dramatic thing that could have happened with this story. So let's see. I think.
Connected at a point.
Pardon?
They are connected at a point. You made it
Well, this is a
wider.
Penrose diagram, right? So the points are spheres, right? Yeah. Incidentally, I can do this experiment where I change the entanglement. Works very nicely here. If I increase the temperature, what happens is that the two sides. So I increase the temperature or increase the entanglement. What happens is that the two sides actually get closer together, and you get a wider throat. If I decrease the temperature, what happens is that they get further apart, and you get a narrower throat. Okay. But there's So I'm drawing. This is the spatial geometry. It's in some sense very important that the full causal geometry looks like this, because these two CFTs had absolutely no interactions between each other, and so something about the dual geometry must preserve the fact that we shouldn't be able to communicate by tinkering with the degrees of freedom in one side. Okay. Okay, so I think that's a natural place to stop. I'll end there for today, and tomorrow I'll get back to saying. So today it was qualitative. Tomorrow I'll do more quantitative things again. Yes.
In some cases, for large n, we know that there are two geometries corresponding to the density matrix. How do you have your two geometries the same conformal boundary come in? How could you see thermal ADS together with the black hole?
Yeah.
In this type of,
Well, so that's an interesting. I mean, there's usually one geometry that dominates, and then some subleading things. So I mean, I think anytime I'm just talking about some single classical geometry, it's important that we're in the large n limit, and so there may be in the dual of this state some other geometries that would be contributing to non-perturbative effects in n, or in finite n effects, and I think the story must certainly be more complicated if we need to go to finite n. 1 over n corrections are probably okay, so we could talk about 1 over n corrections as relating to the behavior of fields on that background, so some semi-classical picture, and that will come up in tomorrow's lecture. But to say something about the gravity side just at finite n, I think it's going to be more confusing. We're going to have to go beyond just having a geometry and some fluctuations on it. Yes?
Your singularity, your firewall,
Yes.
is because each state that you can take as a transplantient problem on the sharp boundary in the whole. It comes from the UV.
You're asking whether that bulk singularity is related to the boundary singularity? Yeah, so there's a...
On the horizon.
Yeah, maybe. Okay, so...
Because of the sharp cutoff of the transplanted.
Yeah, so this is a good... Okay, so this is a good question. There's one thing I was going to mention. So let me... I guess No, I lost my summary. Let me write down again. So for the black hole, I'm going to write down again the summary that I had for, I guess, these hyperbolic black holes. But now I want to think about the Schwarzschild black holes. Okay. So again, I would say that the density matrices on either side correspond to these wedges up until the Schwarzschild horizon. And the entangled state, the full state, corresponds to the two-sided black hole. So the big question is, what if I take a microstate of the CFT on the sphere? Okay. What does that correspond to? Okay. Now, so this is directly related to the firewall debate. Okay, so the old picture would have been that if you have a black hole microstate, okay, it still has some smooth geometry behind the horizon. Here, well, this microstate is just a typical state in this ensemble of states. And the ensemble of states, even this density matrix, we said it doesn't have any information about what happens behind the horizon. Okay? So you might think that if I'm now just talking about a microstate in that ensemble, well, it would be weird if that microstate had information about what happens beyond the horizon, but the ensemble of them doesn't. So in some sense, the most conservative answer to what is the dual of this microstate would actually be that, well, it should be the same conclusion as before. It's no more than this wedge, and what happens instead of the horizon is less clear in this example. So it turns out that we can't, well, yeah, you can't exactly make the same argument that I made before. The geometry is a little bit different. There's not, I can't look at a particular surface and say that its area is going to 0. Nevertheless, you might expect that the answer should be the same, and that there's a different argument that you would have a firewall there. Okay. So it's unclear. The details. Well, okay. So if I tried to apply the same argument, so what? Well, yeah. I mean, let's just apply it. We'll apply Ryu-Takinagi to the entire CFT. We would say that the entropy is 0, and so what it would tell you is that there must be. What it would tell you is that there must be some kind of 0 area surface, which. Well, okay. So what it would tell you is that the sphere is topologically trivial in the bulk geometry. That you could that it's the boundary of something. It would just tell you that it's the boundary of something, and so that would it could be that it's the boundary of something that is singular in the middle, or it could be that it's the boundary of something. Could be a fuzzball. Yes, a fuzzball would do. So I can't argue that there's a firewall in this case as cleanly, but. Yes. Yes.
But
okay.
Are you saying that if I take the 2-point function only on the right, this thing will have on the boundary the Adama, I mean, it has the singularity only on this thing, and if it does not have the analytic continuation of a good Adama 2-point function, when I go on there, I think I will have a generic singularity just because it has to be analytically continued if it is Adama, and if it is a generic thing, it is bad. Like any, is it what you're saying? It's a
Well, I'm not exactly saying that, but I'm not sure. Yeah. So that would be one example of an observable.
On the null when they are null connected. But this singularity, in order to be continued in a good Adama way, it has to be very special.
Yeah. Yeah. So I mean, it's true that that's one of the special properties. One of the special properties of the the entangled state is that you can understand it as an analytic continuation. Yes, but these pure states don't have that nice structure. I mean, they're just some specific state. Yeah. Let me just say one more thing related to this discussion that I thought of. So.
The 2-point function in a pure state.
It should have the same short distance. Sorry, it should have the same short distance behavior.
Up to a boundary, and then you say it can be anything. If it is anything, it cannot be analytic.
Okay, so I'm not sure I completely understand that. The extra thing I wanted to say is so one can actually make an argument for state dependent. So there's been a discussion of the fact that if there is a geometry behind the horizon of these black holes that are dual to pure states, that there can't be some particular operator that will tell you about the geometry that works for every state. That the way that you decode the geometry behind the horizon must be state dependent. And actually, you can give a very simple argument for that here. So let's suppose that. Okay, so we'll suppose that there, for these typical states, and this is basically a similar argument to one that Joe and Don Morolf gave. So let's suppose that there actually is some smooth geometry behind the horizon of these typical microstates. Okay, and let's further suppose that there's some operator that I could use, and I compute the expectation value of this operator in the CFT, and it would tell me, for example, that the stress energy tensor there is small, or any other feature about basically any other property of the physics behind the horizon, which in the standard picture should be the same for all these different microstates. Okay, and so now, okay, so let's say, okay, so for all these different microstates, we can just use this one operator, and it's going to tell us the same answer. Okay, well now I can apply that same operator to the density matrix, and again I'll get the same answer. And so apparently what I would have then done would be to learn something about the physics beyond the horizon from this density matrix. And that was exactly the thing that we argued should not be possible, because I can purify that density matrix in many ways, and you would have different physics beyond the horizon. Okay, so the only way to the thing we could modify then would be to say that there's no single operator. If I have to choose a different operator for every different state, then I can't do this simple argument. And so in some sense, you either have to have, the geometry just ends there, or if you understand the physics behind that horizon somehow, it has to be through a state-dependent construction.
Okay, thanks. Let's make an effort to meet in 15.
Sorry, I didn't want to ask the question.